Hi everybody, welcome to my first project video. This is Mike Rothacker and I'm here to tell you about a really simple amplifier called Ironamp. How simple is really simple? Well, basically there's one transistor and two transformers, and that's pretty much it. So the only thing between your music and your speakers is some iron, some wire, and a single active device. There are no capacitors and no resistors. So how's that for simple? Here's the schematic. We've got an input transformer, a static induction transistor, an output transformer. There's an adjustable voltage source to bias the SIT. This can be a really low current supply, possibly even batteries. And there's a 100 volt B+ power supply. Now let's take a look at how this thing works. DC conditions are set by adjusting the bias voltage so the current through the SIT is around 350 milliamps, which puts the drain at 95 volts or so. The bias voltage is negative, which makes the gate more negative than the source. The more negative we make it, the lower the idle current will be. But watch out, if we don't make it negative enough, the SIT will conduct a lot of current and eventually it will release the magic smoke. For the KD33 grade, you'll need anywhere from -15 volts to -24 volts to set the drain current. The input transformer accepts our music signal on the primary winding, and a copy appears on the secondary, which is attached to the gate of the transistor, which is configured as a common source amplifier and provides voltage and current gain. We've seen this transistor used in low voltage, high current applications, but in this amp, we'll be using it at high voltage, medium current, somewhere between a typical solid state amp and a vacuum tube amp, 95 volts at 350 milliamps. To do this, we need an output transformer to make our 8 ohm speaker look like 150 ohms. An amplified copy of the input appears at the drain of the SIT, which drives the primary coil and gets transformed into the low voltage, high current signal we need for our 8 ohm speaker. Let's take a closer look at the input transformer. It's used for isolation, it eliminates the input capacitor, and improves noise performance. This amp uses the Edcore WSM 10K10K. It's a half-watt matching transformer with a 1:1 winding ratio. You can get them for $10 to $12 at Edcore's website. Other 1:1 matching transformers will work here as well. The input transformer has two windings, a primary, a secondary, and they're wound around an iron core. We can connect the primary in a few different ways, depending on our specific input requirements. There's the 1:1 connection, and the Edcore transformer has a center tap that we can connect to if we need to step up the input voltage a little bit. And we can even have a balance connection. Now let's take a look at our output transformer. We have a primary coil and a secondary coil wound around an iron core. If the primary coil has twice as many windings as the secondary, we say it has a turns ratio of 2. If we connect an 8 ohm speaker across the secondary and measure the impedance of the primary, we see 32 ohms, which is equal to 8 ohms times the square of the turns ratio. We're using the Edcore CX SE25-8-150. It's a 25 watt single-ended transformer. You can buy them for $87 at edcoreusa.com. The turns ratio of our transformer is around 4.33, which gives us a 150 ohm primary with an 8 ohm secondary. I used Sony 2SK82 grade KD33 for this project. Other grades might work, but you probably need a different bias voltage to achieve the right idle current. You can still buy these from circuitdiy.com, and their service is very good. They're $22 each, which is expensive for a transistor, but a nice 300B vacuum tube could set you back $400 or $500. So there you go. SITs have characteristic curves that look a lot like triodes, and they have a couple of interesting properties. The first is called mu, or amplification factor. It's a measure of how much the device will amplify, and it's calculated by dividing the change in drain voltage by the change in gate voltage. For example, a change of 15 volts divided by a change of 2 volts equals 7.5, and that's not a lot of moo. Another interesting property is drain resistance, which is the change in drain voltage over the change in drain current. For example, 6 volts divided by 200 milliamps equals 30 ohms. This is the resistance looking into the drain of the transistor. With triode-like characteristic curves, we can exploit something called load line cancellation to minimize distortion. For this amp, I just moved the operating point around until I found the place where the distortion at 1 watt was just right. The transistor in this project needs a heatsink to keep it cool. The heatsink must dissipate 35 watts at 25 degrees Celsius above room temperature. So the thermal resistance should be 0.7 degrees C per watt or better, and you can never really have too much heatsink. Also, it will need to be drilled to accept a TO3 transistor package. And don't forget to insulate and use thermal paste. Here's a picture of one of my prototype monoblocks. Okay, so how does this thing perform? The gain is only 3 dB with the 1x input. So if you need more, the 2x input takes it up to 9 dB. As for frequency response, the high frequency response is just okay, dropping around 2.6 dB at 20 kHz, which is a lot like mini tube single-ended amps. We're getting a little help here from the input transformer, which has a little bit of high frequency lift. I tried Edcore's 600 ohm transformer, which doesn't have the lift, and of course the response rolls off a bit sooner. At the low end, things are pretty flat to 20 Hz. Noise was under 150 microvolts, and input impedance was greater than 20K with any input configuration. Again, these figures were a little lower with Edcore's 600 ohm transformer. And here's a plot of distortion versus frequency. This is a transformer coupled amp, so we see some increased distortion at the frequency extremes. Here's a plot of distortion versus output in watts. We're down around 0.04% at a tenth of a watt, 0.14% at 1 watt, and 1.2% at 5 watts. I think that's pretty great for a transformer coupled zero feedback amp with 3 parts. All of this might lead you to conclude that this amp will sound tubey, and you'd be right. If you want to learn more, here's some suggested reading. First, Everything by Nelson Pass. His articles are the I Ching of DIY audio. In particular, read his SIT Nemesis article. Also read the book Valve Amplifiers by Morgan Jones. It's amazing, even if you never intend to build a tube amplifier. And the lamp articles at DIYaudio.com. I'd like to thank Nelson Pass for all his help and inspiration over the years. He's been a great friend to our hobby. Also, Jan Didden. Jan does a lot to keep the DIY audio flame burning. You'll want to check out his magazine, Linear Audio. I'd like to thank all my friends on the forums at DIY Audio, with a special shout out to ZenMod. I know he loves Transformers, so I hope he likes this project. And I'd like to say thanks to my new friends at Audio Express. They're working really hard to improve and expand the magazine, and I hope you'll consider subscribing. Okay, just a couple of final thoughts. You should always have an 8 ohm speaker connected to the output when the amp is on. The bias voltage needs to be there before the B+ voltage. Your preamp will need to output 8 volts to get the full 8 watts. If you use the 2x input, then you only need 4 volts. You might even get away with a buffer if your source has enough output. The preamp also needs to have a low output impedance, ideally less than 150 ohms. I'll post a fancy schmancy build in early 2014, complete with a nice chassis, custom power transformer, a meter on the front, and so on. Details will be posted on my blog at audiohobby.com, or you can follow me on Twitter. Well, that's all for now. I hope you enjoyed this video. Now go build something.